And we're going to begin with Danny Wolff, who will talk about energy-based physics for neural networks.
Okay, thanks.
Maybe that's the future. I don't know. Right?
Well, all right. Yeah, thanks for the introduction. So basically, this is going to be a very basic talk, like both in terms of models and in terms of methods, but maybe we can see a little bit what, like Mike said, maybe if neural networks can actually also do something in contact mechanics. But first, I would like to start with giving some sort of motivation of how we can actually use machine learning and especially physics-informed machine learning, and of course with applications to contact. And I mean, the most simple thing that probably pops to mind is maybe to use machine learning as a replacement for a forward solver. So we've already heard something about that before. So when I talk about a forward solver, what I mean is we have some input data. So for instance, boundary conditions, material parameters that we plug typically into some sort of FEM model, and then we run a calculation, we get a solution. If we now replace the FEM model, let's say with a machine learning model, that's what I would call like using machine learning for forward solver. And this is something that has been done, but usually you don't want to stop there because training a machine learning model is usually expensive. So people argue, and it can also be proven with like, if you just do it and train it, that it actually only pays off in certain scenarios, which we can refer to as multi-query scenarios. So basically, you don't want to train a machine learning model once, but you basically have multi-queries, multiple data, say multiple sets of boundary conditions, multiple sets of parameters. And of course, then if you want to evaluate your FEM model for multiple sets of these data, this can become expensive. But if then we would have a machine learning model, this is where we could actually benefit. Another application would be, so to speak, inverse solvers, where let's say we have some incomplete measurements of our unknown solution. We have unknown parameters now that we do not know. We could now construct some sort of optimization loop around our FEM solver, but also here we can actually easier probably solve this with machine learning. Actually, some colleagues of mine already looked into that for very simple problems with linear contact and linear elasticity. Another application that I also would like to mention here is, okay, why do we always, because so far I always talked about machine learning as a replacement for classical FEM, but that's not necessarily what we want to do. So there's another option which I would say is a hybrid solver. Okay, now the pointer, no, okay. Where I would say the idea is to basically combine FEM and machine learning. And this is also something which I will hopefully be able to give you an outlook at the end of the talk. But now the major part of my talk will be on energy-based pins as a forward solver. And the idea behind energy-based pins is closely connected to formulating contact mechanics or continuum mechanics as an energy minimization problem. So how do we do this? Okay, we have like a body which undergoes some deformation. And if this body is equipped with a strain energy density function, we know that the final or resulting deformation of the body is the one that minimizes its total potential energy, or in other words, we require the first variation of the total potential energy to vanish. Now, this total potential energy can be or is composed of an internal energy contribution, which is related to the strain energy density of the body, and to the external energy, which basically comprises surface forces, so tractions, and full body forces. Of course, now the question is, how does contact fit into this? And if we talk about contact, or if I talk about contact, I talk about the most simple scenario where I basically have a fixed and rigid obstacle, unilateral contact. I have a gap function, and I have the well-known Hertz-Signorini-Moreau conditions of frictionless contact. So gap function needs to be greater or equal than 0, the contact pressure smaller or equal to 0, and the complementarity condition needs to hold. So now the question is, how can we get this into a contact, into this energy minimization framework? And of course, also the contact mechanics solution already has, or the contact mechanics community has already some solutions to that. Namely, the idea is to formulate it as a potential and basically penalize deviations of this no penetration condition. And we can, for instance, do this with a penalty approach, where we sort of penalize deviations of this gap function condition in an L2 sense. A little bit about notation. We've also seen that before. So these brackets here is basically this maximum operator. So we take the maximum of 0 and the argument here. Or if we think of a little bit, something a little bit more sophisticated, and we've also already heard about that today, it's basically the augmented Lagrangian method, where we would try to iteratively estimate the Lagrange multiplier field. So we now introduce this Lagrange multiplier lambda here, which we iteratively update, for instance, with the help of Utsawa iterations. So these are now basically two different contact potential formulations that we can now try to integrate with this concept of energy minimization. And now let's talk about what energy-based physics-informed neural networks actually are. And here the idea is very simple. You have a neural network. It can be a very simple neural network, let's say a feed-forward neural network, where we enter as inputs the position vector in our undeformed configuration, and we map this position vector of our undeformed configuration to the displacements of our body. So basically, the neural network approximates what normally would be our PDE solution, and now we try to constrain it by formulating our loss function, our objective function that we want to minimize, with the help of these energy potentials that we introduced before. So we have energy potentials corresponding to the internal and external energy. We have, okay, I didn't talk about that in detail, but in principle, if you have some Dirichlet boundary conditions, you can also impose them in a weak sense, in a least square sense. And of course, you can also include the contact potential. And I want to mention here again, because I unfortunately skipped it earlier, but the point is, of course, this only works if I have a conservative system. So it already excludes a lot of realistic applications because we can't really model friction in this framework. Okay, but basically what we can now do is we can sum up these contributions of the different physical constraints into one total energy potential. And now what we do is we evaluate the integrals because, again, remember all of these potentials, they require integrals over our body or over our boundary. So we evaluate that, and we do that completely as we would do in FEM. So we discretize our body into small elements, and we perform numerical quadrature on each of them. And then in the end, we basically have a loss function, which now depends on these parameters that parameterize our neural network, and we can minimize this potential with respect to the parameters of the neural network. That's the general idea. Now, I said in my talk, okay, I want to talk about nonlinear problems. So in linear problems, going from an initial state to a solution is fairly easy because our equilibrium path is just a straight line. Now, in nonlinear problems, it gets a little bit more complicated. And if you would just apply energy-based physics-informed neural networks the way I just introduced it, what they would do is they would try to solve this in a single step. And actually, they can do this, which I consider very impressive. However, in nonlinear problems, we're typically really interested in reconstructing this nonlinear response of our system. So what we would like to have, or what we would like to do, is try to solve also our problem in multiple load steps so that we get an approximation of this nonlinear response. And now let's have a look of how we can basically modify this idea of energy pins to control the load and to be able to vary the load. And the first thing that I will do is, just for simplicity, I'm going to drop this Dirichlet term. And now, what I introduce is I use a load parameter. So I have this load parameter lambda and the load step delta. And now what we do is basically we check if for a given load parameter, we with this optimization loop, we manage to go beyond some predefined threshold epsilon. And if we manage, then what we do is we increase our load parameters. So we go to the next load step, same as you would do in classical FEM. We increment our load step counter, and we again start from now the important part is what we basically do is we continue training, yes, but we do not start from zero. So we do not start with a randomly initialized neural network, but we basically start also, as we do in FEM, from the solution that we got when this termination criterion was first fulfilled, okay? So this is the general idea. And now with that in mind, I would like to introduce one example here and discuss the result that we have. So we have this quarter of a hemisphere that we subject to a Dirichlet boundary condition on top. So we basically just press it down. Yeah, I'm not going to, or I don't want to talk about this in too much detail because it's very technical, but basically what we do in order to enforce the Dirichlet boundary conditions, we do not enforce it in a weak way. So not with some sort of L2 penalization, but we actually enforce it with an output transformation in our neural network. It's very technical. We can talk about that in detail later if you're interested in it. But that's basically just to omit this term from the total potentials that we're considering. Yeah, we use a moderately large network, and then we discretize this in order with tetrahedral elements in order to be able to compute our energy potentials, and then we compare our solutions to high fidelity FEM results that we obtain with our finite element solver. And now if you look at the training progress of the neural network, it looks something like this. So what we see here is now first for the penalty approach, we use 5 load steps. So you can nicely see these 5 different plateaus here. You see 2 lines basically. So the green line, it's mostly the total energy, right? And you see that it increases over the duration of our loading scenario. And that makes sense because basically every time that we have this jump here, yeah, it means that we increment our load, okay? So by incrementing our load, we introduce energy to the system. So this is why the overall energy increases here. And in orange, you see the contact potential, so this penalty potential. And yeah, so basically, we already get a quite decent L2 error of 3.8 times 10 to the power of -3 in the final load step compared to the FEM solution. And now what we now have is because we reconstruct this nonlinear load path, we get the solutions along it. We can now compare this to the augmented Lagrange version. And now what we see is that basically we again have these steps for the total energy, but now we get these additional plateaus here for the additional Utsava iterations that we have in each load step. And we get a much lower, or like at least by 1 order of magnitude lower error. And again, we also get the progression along the nonlinear load path. Yeah, and we can look at the actual error compared to the FEM reference solution. Am I running out of time, or how much time do I have?
The 4 more minutes.
Okay, perfect. Okay, perfect. I'll get to the end. Okay, so basically what you see here now is the pointwise error compared between the penalty approach and the augmented Lagrange approach compared to the FEM reference solution. And also there, this is now for the Y displacement, and also there that we see that actually introducing this additional Utsava iterations helps us to reduce the error. Okay, yeah, so we also did some investigations of considering this is now for not 5 load steps, for 25 load steps, but basically looking into the maximum gap in order to see also this as a quality measure if we manage to reduce the gap. And yeah, I'm going to skip a little bit over that. We also did some variations of different penalty parameters to see how our methods perform with that. But now what I basically want to is I would like the time to come to a conclusion. And yeah, I hope I was able to show you that with this approach of energy-based physics-informed neural networks, we can get something. I mean, the results are looking nice. I mean, it's a very simple problem, I give you that, but at least it seems to be working as a forward solver. We adapted the learning algorithm so that we have this iterative load control approach, and we are thus able now to also perform augmented Lagrange method with iterations. And just as a last outlook, this is not where we want to stop. Now that we have a machine learning model, we want actually to do something with this. And one idea is, for instance, to use such a trained energy pin as a structural predictor inside the FEM solver. We've already tried this out, not for a contract problem, but like for a simple structural problem. And basically what I wanted to give you as a take-home message is here. Again, the green lines are our machine learning model, and we see that we are able to reduce the Newton iterations by taking such a machine learning model as structural predictor in our FEM solver. Of course, this is just a preliminary result, but it's looking promising, and we hope to extend this also to the contact applications soon. Thank you for your attention.
I mean, regarding sort of the efficiency of this approach.
Yeah.
I mean, it takes a long time to do that. If I think with this 3D problem, I can solve it in 1 minute on my laptop. So, I mean, can you say something about the time?
Yes, yes, yes. So there's a couple of things. I mean, now if we look at this case, so like we are now with a penalty approach, we have 5 load steps, 12 minutes of training time. So it's not too bad. If we Yes, so these are the training iterations. So training iterations for the neural network, but you manage a lot of those within 1 minute. So like again, the whole overall training time on a single GPU is 12 minutes for this example. And I mean, yes, you're right. If you can solve this on your laptop in 1 minute, fair. It's not really comparable. It's about seeing where this goes. And again, like this is now a very simple problem. Okay, the idea is if we understand the methodology, if we're able to apply it to more complex problems, then I guess we can see that it gets more competitive. But I have to say that at least if you compare already this energy-based approach with classical physics-informed neural networks, you're much faster with that one already.
2 questions. The first one is, this is all L2. So did you have a look at boundary stresses and H1 error?
No, but that's a very good point. We can take a look at it. I mean, I didn't show it here. We also compute L2 errors for stresses. So it's not like we're only looking at displacement field. And they are roughly 1 order of magnitude worse, as one would expect. But I didn't look at H1 errors yet.
But this is, and last question, if I may. If you look at the last layer of your network, that in principle should give rise to some basis function you use for approximating the solution.
Yes.
How do they look like?
In our case, linear. So basically,
constructing a linear basis with complex support is your network.
I mean, I'm not sure about the
Yes, I mean it's a piecewise linear approximation. I agree. But how do the basis functions look like?
I mean, like.
Take granular, right?
Sorry, say again.
Take granular is activation function. Which is your activation function?
My activation function in the last layer is linear, but like in the layers before, it's hyperbolic tangent.
Okay.
So like it does. So that's why I was confused because of the hyperbolic tangents. It's not really falling completely into just linear. Yeah.
Okay, let's thank the speaker again.
Do you need the keyboard?
No, I don't think so. Is it okay? So welcome everybody. So I will give a very basic talk from an experimentalist point of view, trying to speak to people who are doing a lot of models. So as an experimentalist, when I do experiment, one of my goals is to compare my experimental measurement to models or to simulations. And it's really important. For example, in this experiment, we measure the shape of a sphere which is in contact with a glass plate using tomography, and we can see the evolution during loading of the shape of this sphere. And we wanted to compare them to a very classical adhesive contact model prediction. In this paper, for example, the authors measure the evolution of the contact radius as function of the normal force during a contact experiment, and they vary the velocity of the contact. And at the end, their goal was to compare this with a new adhesive viscoelastic contact model. So if you want to do those comparisons in an accurate way and in a robust way, of course, you need well-designed experiments, which is the case, I hope, here. You need a good model, but you also need something very basic. You need your parameter value to be very quantitative and to have very nice value for simple parameters such as Young modulus, adhesion energy, Tabor parameter. Alice spoke about it this morning. So all those parameters are very important. So we get back to a very, very basic questions. From a contact experiment, measuring the evolution of the normal load as function of the contact radius, either during loading or unloading, is it possible to perform a simple fit of this curve and to get back to your Young modulus, adhesion energy, Tabor parameter, why not a Poisson coefficient of radius of your contact? This is the basic things you need if you want to compare your experiment with simulation. So to do those fits, of course, I will need some models. So you saw them this morning, but the classical models in adhesive contacts are the one from DMT on one side of the adhesive regime, so DMT for stiff and weakly adhesive materials. The other one is the famous JKR models, which relates, again, the contact radius to the normal force, which is more applicable for compliant and adhesive material. And what I think is more interesting, you have the model proposed by Mojis based on the Dugdale approach, which introduce the Tabor parameter, which allow you to to have a nice transition between DMT regime to GKR regime, thanks to this parameter. And again, you have an expression that links the evolution of the contact radius as function of the normal load. So, starting from those three kind of model, we propose two new fitting methods. I will show you them in a few slides. And we propose to benchmark them against the classical method you use to extract material parameter from your contact experiment. So first, of course, we use the classical DMT. So we do a fit of data using DMT. We use the same with the GKR equation, which is proposed here, which again involves also the adhesion energy. We use a method that is, for experimentalists, very used in literature, which is the one proposed in this paper by Chowdhury. In fact, it just rearranged the GKR equation in a certain manner using those kind of normalization of the normal force and of the contact radius, allowing to have a nice linear version of GKR equation. And if you plot those normalized value, once again, the other, you see that in the GKR regime, you have a nice linear behavior. So you can do a linear fit on your data, except which is a little bit more complicated than using this power equations. The fourth one, sorry, we use is a method proposed by Karpik in this paper in 1999. He used an approximation of the Mojis-Dugdale model, and he proposed a transition equation which can go from DMT to GKR using a new parameter alpha, a single parameter alpha, so you can have a relation between the normal force and the contact radius just using a single parameter all along the different adhesive regime. And then he proposed three empirical relations to go in a sequential step from alpha, this new parameter you extract from your data, to lambda, the real Tabor parameter of Mojis-Dugdale model. Then from lambda, you can compute the adhesion energy, gamma here, and W in the rest of my presentation. And then from lambda and gamma, you can compute the Young modulus. So the calculation of all the parameters is sequential. And if you have some error on the first one, you can imagine that you will propagate the error all along the methods. So the two new fitting methods we propose are also quite simple. The first one is just simply using directly the model proposed by Mojis, which is not quite easy on our computer and which was not easy a few years ago. That's why Karpik proposed an approximation method, because he was not able to compute this little bit complicated equation at the time. And so this is a fit which we call Mogis-Dugdale on raw data, just on A versus P data. And the most interesting one, as you will see, is the one performed, but not on raw data, but on normalized data using the normalization I show you, which was proposed by Chowdhury in his paper. Why do we do that? It's because if you plot the normalized version of the normal force against the normalized contact radius with the normalization proposed by Chowdhury, you see that the GKR is linear, but if you go down the Tabor parameter to DMT, you see that there is a cutoff that appears at low lambda, and this cutoff is really interesting if you want to fit your data because it's quite easy to capture. Whereas if you just plot A versus P, you see that the modification in your curve are really tiny and really difficult to capture. You will see that in a few slides. So to test those fit methods, we create a data set. So a data set is just an evolution of the normal load as function of contact radius. We did that for different kind of material and different value of Young modulus, adhesion energy. The idea was to have a largest possible range in terms of the Young modulus times the radius of curvature divided by the adhesion energy, which is the dimensionless parameter in contact experiment. So this is the kind of curve we want to fit. So here there is just a vertical shift in order to see the difference going from GKR in red to DMT in blue. And what we did also is to compute those curves down to zero contact radius, which is not physical because you will, as an experimentalist, encounter instability. So we do a complete data set and a truncation at the load control instability, a truncation at the displacement control instability, and one a little bit further just to mimic experiment on which you were not able to go down to the stability, which is easy for a model, but quite difficult for experimentalists. You can see that at high Tabor parameter, the truncation has an important effect on your curve because you lose nearly all the negative part of your curve. At low Tabor parameter, so close to DMT, the truncation is quite insignificant. So let's look at the results. So here is a fit with classical DMT and GKR equation. So this is the evolution of the this is the Young modulus predicted by GKR equation in yellow and in violet or something like that for DMT. So the black circle corresponds to the expected value. Here is the Young modulus as function of the different truncation I just presented, and here is the adhesion energy as function of the different truncation. So the advantage of these two fit methods is that they are really easy to implement. They give quite a good result for the extreme value of lambda, of course, GKR for large lambda, DMT for low lambda. But in the middle, you don't have access to your value. So you don't know, you are not able to capture what happened in the middle. So as an experimentalist or as a user, you have to guess which equation is better for you to compute your data. And most importantly, there is a high risk of what I call false positive. Here you see, you may see that as a dashed line, this is the fits that are performed. You see that the fit for GKR model works quite well at large lambda value. But if you look here, when you have truncation, you can see that the fit seems correct. If you look at your R square, the R square is really high, really close to 1. But if you look at the data for lambda equal 1, you see that there is a huge error on the Young modulus. There is a large error on the adhesion energy, so your estimation of parameter is totally wrong, even if you seem to have performed a fit which is correct. This is nearly the same when you use the method proposed by Chowdhury, which is only available again in the GKR regime. So when you are in GKR regime, the fits are linear. They work quite well. But if you go down to lambda, closer to DMT behavior, you can see that if you have the full data set, of course, your fit is totally wrong. This is easy to see. But again, this is not physical. But if you have truncation of your data, you may think your data are linear. So you may think you are in a GKR behavior. So you may think that you extract the good value for your experiment, but in fact, there is a huge error on Young modulus and also on adhesion energy. So you really have to take care that your data go down to a very low contact radius, as close as possible to the instability point, because everything that will give you an information on the adhesion regime is somewhere here at very low contact radius. So now, if you use the method proposed by Karpik, so the data has these light blue curves, the advantage is that it's based on the Mogis-Dugdale model, so you can capture the Young modulus and the adhesion energy, and also the lambda parameter in all the regime from DMT to GKR. There are still some errors in the intermediate regimes that may result from, I say there is an empirical relation, so this is not the real Mogis-Dugdale model. And as I told you before, there is a risk of propagating error due to the sequential method that is used. So, and now if you go to the two new fit method we proposed, you can see the red curve and the bold black or blue curve here. You can see that, again, we capture all the lambda regime. You don't need any guessing of your adhesion regime. So you will compute your adhesion regime. So you will compute quite nicely the evolution of in your system. Fit performed with the normalization are nearly perfect. You can see that a tiny difference between the result and the expected value for all those blue curves, maybe a little bit here at high truncation for high Tabor parameter. And why is this fit very performant? It's because, as I told you, you can capture very well the cutoff at low contact radius with this method, so you don't have any false positive. Your fit are nearly perfect. The R square is often equal to 1, and there is no error, and you really get information from this part of the curve, which is the most important for, again, for experimentalists. So this method seems to work quite well. We want to test its robustness against noise, because if you do experiment, of course, you will have noise on your data. So we introduce some noise in our theoretical data set. So either on the load, either on the contact radius, or on both the load and the contact radius. And you can see that here I just presented the three methods based on Mogis-Dugdale model. You can see that you get nice results. There is nearly no sensitivity to noise level, especially with this new method based on Mogis-Dugdale on normalized data. Maybe the only thing is that at low lambda, here it's for lambda close to DMT, so 0.001, lambda is quite not so nicely captured by these new methods. This is because when you add noise, the noise is amplified by the normalization at low contact radius, where I told you there is the information you need to really capture the adhesive regime and the value of your parameters. So using this new method, you can accurate and robust results. So the results are nearly the same for all the different materials we have tested. So here it's for ultra soft gel, or here for rigid polymers. the fit method based on Multi-Dugdale model allow to capture the Tabor parameter for all adhesive regime. You have not to guess before your experiment that you are either in GKR model or in DMT regimes. And the results with this new method are nearly perfect. The code is nearly ready to be shared on my GitLab in a few weeks, I guess. Thank you for your attention.
Very short question, maybe. Yeah. Go back there first. Go ahead.
Well, I am just curious. Do you think that your approach may be affected by the scales? What I mean is that, do you think that, for example, when you do indentation with the FM, that this typically very noise?
I don't think so. I don't show you. In the different material we have simulated, the one for rigid crystalline solid corresponds to a kind of IFM experiment. So I use a very low radius of curvature, 20 nanometers, which is the typical IFM type curvature. Everything works quite well. There is a little trick in the function. Yeah, I use a rescaling parameter, which is a little bit hidden, but if you rescale a little bit, everything works quite well.
You want to answer this quick?
Yeah, I was just wondering when you have this reference value that you're comparing with, how did you get it?
I just apply the Multi-Dugdale model for different range of radius of curvature and calculate the normal law.
Great. Yeah, thank you, speaker again. Our next speaker, Gabor, we'll be talking about there's word lunar friction.
Thank you very much. My name is Gabor Csernak. I'm from the Budapest University of Technology and Economics. This is a joint work with my PhD student Balázs Békési, and I will talk about interesting solutions that we found in a simple mechanical model with Lugre friction force. The Lugre model is widely used in multi-body dynamics. However, originally it was introduced for control applications, and no wonder that the analysis of this model often focused on systems theoretic aspects. In my presentation, I will strongly keep a mechanical perspective. We embedded the model in a simple mechanical model and performed a nonlinear dynamical analysis. We found several complicated bifurcations, and I will show you many parameter domains where there are multi-stable solution possibilities. And in the end of the presentation, I will talk about the passivity, namely in certain cases, the Lugre model is such that the friction force generates energy. So I will discuss the mechanical implications of this, and I will talk about the connection between the passivity and the limit cycles that can occur in the system. The original Lugre model can be interpreted based on this figure. So we have a body that moves with velocity v, and we have a bristle, and the bristle deformation is denoted by z. We have a friction force F that is a linear combination of the z bristle deformation, the z deformation speed, and the v, the velocity of the body. We also have a differential equation that describes the dynamics of the bristle. And here we have this g of v function. This is the Strybeck characteristic that describes the transition between the dynamic and static friction forces. And here we have a Vs Strybeck velocity parameter and the delta Strybeck exponent parameter. I think that this model has a drawback, namely, here we have two parallel but opposite coordinate systems. The velocity is positive, it is pointing to the right, z is positive to the left. And if you are not careful enough, when you want to extend this model to 2 dimensions, then it can happen that you end up with a left-handed coordinate system, and we would like to avoid it. So I suggest a small modification in the equations. So here, every direction will be pointing in the same direction. As a consequence, certain signs will be changed in the equations. And I must admit that I always mixed which sigma means what in this equation. So I introduced other equations that are more fit to the mechanical meaning of these parameters. K will be the stiffness of the bristle. A lowercase c will denote the damping of the bristle. And the uppercase c will be the viscous damping parameter. I also changed the notation of the Strybeck characteristic to S. I think it will be easy to remember, and FF will be the friction force. This is the very, very simple mechanical model. We have a block of mass m. It slides with velocity v under the action of an external force Fe and a friction force Ff. So these two forces will appear on the right-hand side of the equation of motion. And the remaining equations describe the Lugano model. If we divide the first equation by the mass and introduce a dimensionless time and dimensionless space, then 3 parameters can be eliminated, and we obtain dimensionless equations. Here, 3 parameters, the lowercase c bristle damping, the capital C viscous damping, and the external force Fe will be considered as bifurcation parameters, while the other 3 parameters that remained in the Strybeck characteristic will be considered to be fixed. In the first step of the analysis, we wanted to find the equilibria of the system. And first, we considered the differential equation of the bristle deformation. From this, you can see that if z dot is 0, then either the velocity is 0, or we obtain a condition for the bristle deformation that is given by the Strybeck characteristic. The second condition of the equilibrium is that v dot equals 0. And I don't want to go into the details since it is quite trivial that there are basically 2 cases. Either the velocity is 0 and we have sticking, or the velocity is non-zero and we have slipping equilibrium solutions. And this equation describes the slipping equilibria, which is, again, quite trivial. So one part of the friction force is given by the Strybeck characteristic, other part is given by the viscous friction, and here we have an external force, and these are in equilibrium. It means that we can find the slipping equilibria if we search for the intersections of this C times V minus Fe line, this dashed line here, and the Strybeck characteristic, which looks like this. You can see that the shape of the Strybeck characteristic depends strongly on the Strybeck exponent delta, and it means that also the number of possible equilibria also depends on the exponent. The most interesting case is when the exponent is larger than 1. This is shown here. So these are phase portraits. We have 2 state variables, the velocity and the deformation of the bristle. The blue curves show the Strybeck characteristic, and the green line is the line that corresponds to the viscous damping and the external force. If the external force is small, then we obtain one equilibrium here at 0 velocity. It is a sticking equilibrium. And if we increase the external force that pushes the body, then this line will be shifted downwards, and at a sufficiently large value, we obtain a slipping equilibrium point, and a sticking equilibrium point also that is unstable. But the intermediate cases are more interesting, since it can happen that 2 slipping equilibria occur, plus a sticking equilibrium. Or it can even happen that we have 3 slipping equilibrium points and an unstable sticking equilibrium. Since there are so many equilibria, we denoted them according to the velocity. So here, the larger index means that the velocity is larger. So this Y3 will be the quick, the fast slipping solution. Y1 will always denote the small velocity solution, and Y2 will be always an unstable solution that is a so-called saddle point of the system. I would like to remark that the appearance of this Y1 means that we have a very, very slowly moving solution. And in numerical approaches to this problem, it can be mixed up with a sticking solution. So it can lead to problematic solutions. Just to show the other case, if the exponent is less than 1 or just equal to 1, then due to the shape of this stable characteristic, only 2 slipping equilibria can coexist. The previously shown cases can be identified even on the parameter plane of the viscous damping and the external force. And viscous damping and external force. If you take into account that the stability can be examined based on the characteristic equation of the linearized system, and if the Bristol damping is considered to be 0, then it turns out that only the constant term of the characteristic equation is what counts, since this is the stronger condition. And so we obtain bifurcation curves that split the parameter domain into several subdomains. Here in D note, we don't have any slipping equilibrium. In D1 or D3, we have only a single slipping equilibrium. In D2, 3, and D1, 2, 3, we have 2 or 3 slipping equilibria, respectively. But the problem becomes more complicated if we introduce positive Bristol damping, since in this case, the A1 term here in the characteristic equation will be also important. And it turns out that if the Bristol damping is too large, then Hopf bifurcation can occur. So now we have a 3-parameter space, a 3-dimensional parameter space. Capital C is the viscous damping, the Fe external force, and the lowercase c is the Bristol damping. And here, the level curves of the Bristol damping are shown where the Hopf bifurcation occurs. So this is basically a surface in the 3-dimensional space, and this surface folds back to itself. And the left-hand side shows the Hopf bifurcation level curves at the small velocity equilibrium. And on the right-hand side, we see the Hopf bifurcation surface sees the level curves for the high velocity slipping equilibrium. Just what does it mean? So what happens after a Hopf bifurcation? Via Hopf bifurcation, so-called limit cycles occur, which basically means that there is a fluctuation in the velocity, so the block moves forward, but the velocity will be larger or less during the motion. Okay, at this point, we had to check the passivity of the system as well, since from systems theoretic perspective, the friction model can be considered as an input-output system. The input is usually the velocity, and the output is a force, for example, the friction force. And from mechanical point of view, the dissipativity is what really counts. So the input energy to the system must be always greater than the variation in the mechanical energy. But the passivity criterion that is given in the framework of the systems theory is more strict, since it means that the dissipativity must be fulfilled for all possible inputs. It basically means that we can prescribe the velocity, and the system must stay dissipative still. Okay, the passivity formula was derived in 2000, so it means that the Bristol damping must be less than this expression if we want a passive system. However, let me mention that in this paper, they report experimental results. Actually, only one result is reported, and in that case, the Bristol damping is 6 times bigger than this limiting case. So it means that if we are in a non-passive parameter domain, it will not defy the laws of physics, perhaps. But still, a too large Bristol damping violates the passivity. So we wanted to know how are the dissipativity, the passivity, and the Hopf bifurcation related. I will show you a couple of examples. Here, the Bristol damping is 7 times bigger than the limit, and they're near a subcritical Hopf bifurcation, which means that we have an unstable limit cycle here near a stable slipping solution. We could identify the zone. Here, the dissipativity is violated, but you can see that this limit cycle doesn't enter this zone, so it can physically realize. Example, we can have even a supercritical, which means that we have a stable limit cycle and a unstable slipping solution. You can see again that this does not enter the problematic zone. Third example. Now you can see that this case is even more complicated, since here we have a global bifurcation, a fault bifurcation. Near the stable solution, we have an unstable limit cycle. There is an even greater stable limit cycle around it. Although that the dissipation zone, it is not far from it, so it can be also already a dangerous situation. And the last example is a really extreme case. Now the Bristol damping is 49 times bigger than the limit, and indeed non-dissipative zone is here, and the solutions enter it. But from non-linear dynamical point of view, this is the most interesting case, since what we see is here we have a stable solution, and there is an unstable limit cycle around it. In that corner, there is another stable point, and a tiny limit cycle around it, and everything is encircled by a big stable limit cycle. In the examples that I showed you, the system was non-passive, and there were Hopf bifurcations. So the question arises, is Hopf bifurcation possible at all if we are at passive parameters? So we wanted to check it, and basically we are searching for a Bristol damping that is below the passivity limit, but above the Hopf bifurcation limit, which can be expressed with the Strzebek characteristic. This inequality can be expressed like this. The left-hand side is positive, and the question is, can the right-hand side be positive or not? So this expression is the critical one, since the exponential function can grow very quickly. And it is easy to see that it has a minimum at v equals 1. And if we substitute v equals 1, we obtain this inequality, which basically means that Hopf bifurcation and limit cycles can occur in a passive system if the Strzebek exponent is larger than the base of the natural logarithm, that is 2.71 approximately, which is rare, but now it is checked. And here is an example where we are really below the passivity limit, but above the Hopf bifurcation limit, and we have a limit cycle, and the system is passive. So the results can be summarized as follows. we proposed a new dimensionless formulation for the Lugano model. We performed a 2 and 3 parameter bifurcation analysis. We found monostable, bistable, tristable parameter domains with limit cycles. And the take-home message can be this, that we found very, very small domains of attraction and slowly slipping solutions. So it can lead to numerical challenges in this system. And we also analyzed the passivity and dissipativity of the system and showed that Hopf bifurcation can occur if the Strebeck component is larger than E. So thank you for your attention.
I have one. Is this mainly only good for 2D? Is it?
Pardon?
Can you do it in three dimensions?
I didn't. Certainly.
Is there versions of it that people have done in 3D?
This kind of analysis was not done yet in more dimensions, but we would like. Actually, we did it with other friction models, but I mentioned the problem with the left-handed coordinate systems in the beginning because I read really papers where people wanted to extend the Lugano model to 2 dimensions, and somehow the coordinate systems were mixed up, and I saw that sometimes it is left-handed. Because according to the original Lugano model, the velocity components are chosen first. So in a certain situation, it can be that this is Vx, this is Vy, but if the velocity points in another direction, then the coordinate system flips.
Yeah. More questions? Where would I use this type of model? What applications?
The Lugano model is often used when the motion of robots is analyzed. Actually, this model was developed by control people, and I must say that this differential equation that they give does not comply with the Newton's laws. So from this perspective, this passivity issue is also kind of questionable, but it is very, very often used in multi-body dynamics and in the analysis of robots and other control systems.
Because regular Coulomb friction doesn't get them right.
Yes, for example, it is usual that the velocity is varied periodically. And it turns out that in that case, they have a so-called frictional lag. So if this is not very good. So let's say this is our Strebeck characteristic, and here is the velocity, and this is the force that we encounter. And if the velocity is varied, then it was found that the system remains close to the Strebeck characteristic, but it goes around a loop. And this is what the Coulomb friction law doesn't know, but with the Lugano friction model, it can be reproduced numerically.
You see that in real physical systems, that's true?
Pardon?
You see that in a real physical system?
Yes, it is an experimental result.
What kind of materials are we talking about that are coming in time?
That's a very good question, since just because of this model was used to describe the motion of robots, it is not so simple that we talk about materials. The whole robot is inside it. So our mechanism is inside the robot.
I see.
And
right at the surface.
yes, so it is something complicated that is described by this very simple differential equation.
We have any more questions? Okay, well, let's thank the speaker.
Thank you.
Coffee break?
Yep.
So